Okay, this tutorial will be going over the ideal gas law and kind of like the background for the ideal gas law. So there's a lot of theory. So before we go into the ideal gas law, we have to kind of figure out what's defined to be ideal. So there's several postulates of what's called the kinetic molecular theory, which ultimately describes the behavior of gases. And then I'll try to explain each one of these postulates and the implications of each one. Okay, so gases consist of large numbers of molecules that are in continuous random motion. So an application of this is when a gas is in a let's say you have a room, and then you have like a really pungent gas, like a really strong odor, like really strong, like you open up a very strong perfume or cologne. Well, this gas molecule will start traveling all around the room, okay, in some random order. Okay, and if you so students or like people on this end of the classroom, okay, on this end of the classroom might smell the gas before some students over here. If you saw the way I drew the path of this gas molecule, it went up here first. Okay, so let's say you did this again. Okay, like a day later you did this again. Okay, you would have the gas molecule might travel this way. Okay, and then do some crazy motion this way and then this way. Okay, and then it may like hover around here for a while before it decides to go down here. Okay, so the people over here would smell the gas first, then over here, and then everybody over here, because the gas decided to stay over here, might smell the gas then. So that's what it means by continuous random motion. Okay, and by molecule, it may also mean like a monatomic gas like helium or neon. Okay, as well as polyatomic gases like N2O2, SO2, NO2, gases like that, CO2, more than one atom. Okay, so the volume of a gas molecule themselves is said to be negligible. So the what this means is, and this is in relation to, actually, hold. Okay, so this is in, or we'll say relative to the container the gas molecule is in. So if you have like if you have, so it's if you let's say you have like a canister, okay, some can, and the gas molecule themselves are, I mean, we're talking like the size of atoms and molecules here compared to the size of like a 2 liter container here. So now this one's going to have an important role when pressures or volumes become really small. Sometimes you'll see that when a gas is not behaving ideally, you'll see that the molecule themselves, the actual gas molecule, will actually have a volume, and you have to factor that in. So, of course, as I state these postulates, there are of course gray areas, okay, or areas where these actually break down. These postulates are no longer true. If they are true, we're allowed to safely use the gas laws, and they work. So, so let's go on to the next one. So it says attractive and repulsive forces between gas molecules are negligible. Okay, so what that means is if I have a gas molecule, if I have a container of gases, like let's say we have CO2, and we know this to be nonpolar, and the type of forces it would have are London dispersion forces. So we all know dry ice is solid CO2. So at some point, CO2 molecules are going to have attractive forces and form liquids and solids. However, if we assume that the attractive and repulsive forces are negligible, then the CO2 molecules, okay, are free to roam around here without being inhibited by other CO2s. So there are no attractive forces happening between these CO2 molecules. Okay, so this is a potential attractive force, and they don't happen. Okay, if there were attractive forces, okay, if there were these would be called IMFs. If there were IMFs, then it wouldn't the gas wouldn't collide with the container, and it wouldn't cause pressure as it's predicted. It wouldn't cause it wouldn't show temperature. It wouldn't show yeah, it wouldn't cause collisions. And if it were a flexible container, it wouldn't change in volume either. Okay, so it wouldn't behave like a gas anymore if they were attracted to each other. It would actually start becoming a liquid, which is not a gas. So the next one, energy can be transferred between gas molecules, but does not affect the overall kinetic energy of the sample. And so energy can be transferred between gas molecules, but does not affect the overall average kinetic energy of the sample. So this another way to state this is that the gas collisions are said to be elastic. So after a gas molecule collides with another gas molecule, they don't lose any. The overall the overall energy transferred remains the same. So the only way to really change the kinetic energy is the next postulate is by changing the temperature. So you have to change the temperature to affect the kinetic energy of of a sample of gas molecules. Um, Even if you change the gas molecule itself, so let's say you use like a bigger gas molecule, and you'll think that okay, since it's bigger, it's going to move slower, but this is not. But when you factor in kinetic energy, you also have to consider the mass. So you have to consider the mass and the velocity that the gas is traveling. So if you use a bigger gas molecule, it may be moving slower, the velocity, but the mass would be bigger. So when you multiply the two, you would get the same kinetic energy. So the only way really to change kinetic energy is to change the temperature. So even when they collide with themselves and the sides of the container, it doesn't change kinetic energy. Okay, the average kinetic energy of the molecules is proportional. So on to postulate 5, the average kinetic energy, so I'm using this symbol, of the molecules is proportional to the absolute temperature. At any given temperature, the molecules of all gases have the same kinetic energy. So this is what I was saying. These two are related here. So if I have this gas, okay, the velocity may be fast, but the mass might be smaller. Versus if I have this gas, okay, the velocity may be slower, but the mass is much bigger. Okay, so that won't affect the kinetic energy. So again, the way to affect kinetic energy is to change the temperature. Okay, in terms of our problem solving, okay, these are going to be the most important postulates is this one and this one. Okay, because there are times when these two postulates actually break down for gases. Okay, and it's affected by also this kind of plays a role as well. So if you start changing the temperature, if you start changing the temperature of a gas, okay, they'll start to move slower, and if the gas starts moving slower, okay, so if you start messing with postulate 5, then you're going to make the gas molecules move slower, and if they move slower, they have more of a chance to have attractive forces, and therefore we all know that if we put liquid water into a freezer, we're lowering the temperature, so they're going to be moving slower, and then they're going to start to exhibit attractive forces, and it will no longer be a gas. Okay, so it will no longer do any of these things. Okay, if we cool it down. Okay, so in a way, one of the most important postulates is 5. Okay, however, when we look at the gas laws, okay, these two and 3 are going to play an important role, okay, in the gas laws along with 5. as well. Okay, so I could actually let's go ahead and highlight this one too. Okay, so along with 5, absolute kinetic, absolute temperature. Okay, so by absolute, I mean literally absolute. So like on the Kelvin scale. So that whole scale was devised to account for any negative temperatures that a gas might have. So when we're using the gas laws, you should be working with kelvins to avoid having negative volumes or negative pressures, which physically can't happen. Okay, so that's the whole reason the absolute temperature scale was devised, was so that it was based on the coldest known temperature, which is 0 Kelvin.